This is Srikanth S, Assistant Professor of EEE Department. Today I am discussing the concept of series RC and RLC circuits using AC excitation. And first we will go with the series RC circuit. Here we are making the resistance and capacitance in series. So the current flowing through the series elements is same. So the current is same in the series elements. These two are connected in series. So here we are going to get VR voltage across the resistor with this terminal positive and this terminal negative, and VC this terminal positive and this terminal negative. So here we are giving the voltage as V, which is equals to Vm sine omega t. Vm sine omega t. So here in the when the resistance and capacitance are connected in series, when the resistances and capacitance is connected in series, we are going to get the voltage is we are giving, that is V is equals to Vm sine omega t, I is equals to Im sine omega t plus phi. So here how we are going to get this, what is the value of phi? Let us see. Here voltage V is equals to V square root of VR square plus VC square. VR square plus VC square, because we are going to get in the vector form. So what is VR? VR is equals to I into R. That is current flowing through the resistance multiplied with the resistance. Whereas VC is equals to I into XC. I into XC. That is the reactance of the capacitance, where XC is equals to 1 by omega C. That is equals to 1 by 2 pi FC. 1 by 2 pi FC. So V is equals to square root of IR square plus IXC whole square. If you take V is equals to, if you take I common, we are going to get square root of R square plus XC square. R square plus XC square is nothing but Z, that is impedance of the circuit, where Z is equals to square root of R square plus XC square. And here we need to calculate the phase angle. The phase angle phi is equals to tan inverse of VC by R. Here phi is equals to tan inverse I into XC. VC is nothing but voltage across the capacitance, that is I into XC by I into R. I will get cancelled. We are going to get XC by R. That is, from this we are going to get phi is equals to tan inverse of 1 by omega CR. Phi is equals to tan inverse of 1 by omega CR. So here this is the phi value, and here it is a capacitance. So the current will be leading, that is I is equals to Im sine omega t plus phi. So here first let us go with the phasor diagram. That is, phasor diagram is, here we are drawing VR, and here capacitance voltage will be, that is lagging behind the VR by 90 degrees. Lagging behind the VR by 90 degrees. And here we are going to get the voltage as, here the capacitance voltage will be lagging behind the 90 degrees. So the resultant voltage will be, this is the resultant voltage with the phase angle of phi. So here the I value will be leading. I value will be leading the voltage by an angle of phi. So I is starting before the voltage 0 point. The 0 point of current will be starting before the voltage starting point. That's why I is called leading. So we can call it as in the RC series circuit, current is leading the voltage V by an angle of phi. And we can also write this one as the voltage is lagging current by 5 degrees. So these are the two statements we can give corresponding to the waveforms of the RC series circuit voltage and current. Now let us go with one example. A capacitor of capacitance 79.5 microfarad is connected in series with the non-inductive resistance of 30 ohms across 100 volts 50 hertz supply. Find impedance, current, phase angle and equation for the instantaneous value of current. So in this, the data given is capacitance value is given, resistance value is given, voltage and frequency values are given. We need to calculate what is the impedance, current, phase angle and equation for the instantaneous values. So for calculating impedance, R is already we are having, and we need to calculate what is the reactance of the capacitance. So here the reactance of the capacitance XC is equals to 1 by 2 pi FC, that is equals to 1 by 2 pi value is 3.14, 50 is the frequency, and we are substituting the capacitance value 79.5 microfarad, 79.5 into 10 to the power of minus 6. Here we are going to get the value as 40 ohms. Here we are going to get the value as 40 ohms. And the impedance is equals to Z is equals to square root of R square plus XC square, which is equals to square root of R value is given as 30 ohms. R value is given as 30 ohms. 30 square plus XC value is, we got it as 40 ohms, that is 40 square, which is equals to 900 plus 1600 square root of 2500, that will gives a value of 50 ohms. And after getting the impedance, we can calculate the current, because current in both the elements is same. So I is equals to V by Z. I is equals to V by Z. That is equals to 100 by 50, which we are going to get it as 2 amperes. We are going to get this value as 2 amperes. And phi is equals to tan inverse of XC by R, that is equals to tan inverse 40 by 30, which is going to have a 53 degrees, and this value will be leading because whenever we are having capacitance, the current will be leading. So that's why the phi value will be writing it as leading. And in order to get the Im and Vm values, in order to get Im value, we have to multiply with root 2. Whatever the RMS values we got, that should be multiplied with root 2 in order to get the maximum value. So the maximum value is equals to root 2 into I, that is equals to root 2 into 2, which is equals to 2.828 amperes, where omega is equals to 2 pi f, that is 2 into 3.14 into 50, that is equals to 314 radians per second. So I is equals to 2.828 sine 314t plus 53. So this is the instantaneous current equation corresponding to the RC series circuit. And the next, we need to calculate the voltage and current across the RLC series circuits. So here, voltage, when we have connected the three elements R, L, C are in series. V, R, L, C are connected in series. When the elements are connected in series, current is same, and voltage V, which we are giving, is V is equals to Vm sine omega t, Vm sine omega t. And here the voltage is divided into three times. Three, that is VR, VL, and VC. And VR, VL, VC, always VL will be positive, VC will be negative. And here we are assuming that VL value, inductive voltage, has higher value. So that is VL minus VC, we are going to get that across the LC series combination, we are going to get the resultant voltage will be VL minus VC, because here we are assuming that VL value has higher magnitude. VL value has higher magnitude. So which is equals to V is equals to square root of VR square plus VL minus VC whole square. So V is equals to square root of IR square plus I into XL minus I into XC whole square. Here if you take I common, we are going to get square root of R square plus XL minus XC whole square. From this, V is equals to IZ. V is equals to IZ, where impedance is equals to square root of R square plus XL minus XC whole square. And here the phasor diagram is, this is the VR phasor, this is the VR phasor, and VL phasor will be 90 degrees leading and VC phasor will be 90 degrees lagging. Here the resultant phasor, we are taking it as VL minus VC. So that will be in the inductive side. So here the voltage, resultant voltage will be V. We are going to get with the phase angle difference of phi. And phi is equals to tan inverse of VL minus VC by R. Tan inverse of VL minus VC by R, where phi is equals to tan inverse of I into XL minus I into XC by IR. So II will get cancelled, will get XL minus XC by R. And here it is. This is a phi, and this phi is used to calculate the power factor. And here we have taken the inductive voltage has higher value, so phi will be lagging. Phi will be lagging. Okay, so here the phi will be lagging behind the voltage V. Now we'll go with the problem. A 230 volts 50 Hz AC supply is applied to a coil of 0.06 Henry's inductance and 2.5 ohms resistance connected in series with a 6.8 microfarad capacitor and calculate impedance, current, phase angle between current and voltage, power factor and power consumed. So here the given data is resistance value is given, inductance value is given and capacitance value is given and voltage frequency values are given. So from this we are going to calculate all the parameters corresponding to the given circuit, where here first in order to get the impedance value, first we need to calculate the reactance of the inductor and reactance of the capacitor, where XL is equals to 2 pi FL, which is equals to 2 into 3.14 into 50 into 0.06, which is equals to 18.84 ohms, and where XC is equals to 1 by 2 pi FC, which is equals to 1 by 2 pi into frequency value is 50 and the capacitance value is 6.8 microfarad, 6.8 into 10 to the power of minus 6, and here we are going to get 468 ohms, and here capacitive reactance value has higher magnitude. So here Z is equals to square root of R square plus XL minus XC whole square, XL minus XC whole square. So R value is given as 2.5 ohms. So the value is 2.5 square plus 18.84 is the inductive reactance we got, that is 18.84 minus 468 whole square, minus 468 whole square, which is equals to 449.2 ohms, which is equals to 449.2 ohms. Now after getting the impedance, we can calculate the second parameter. What we need to calculate is the current. So the current is equals to V by Z. Here the RMS value of voltage is given as 230 volts divided by Z value is 449.2, which is equals to 0.512 amperes. Now the current is completed. Now we need to calculate what is the phase angle difference between current and voltage. So for that, phi is equals to tan inverse of XL minus XC by R. Phi is equals to tan inverse of XL minus XC by R, which is equals to tan inverse of 18.84 minus 468 by 30, that is equals to minus 89.7 degrees. This is the phase angle difference between the voltage and current. Here we got minus means the phi value is leading. Here whatever the phi value we are getting as negative means we are going to have the power factor will be in leading condition. Power factor will be in leading condition. Now in order to get the power factor, we have to substitute in cos phi, that is phi value should be substituted in place of phi in cos phi. So power factor is equals to cos phi, which is equals to cos 89.7. We are going to get this value as 0.0056 leading, and power P is equals to Vi cos phi, that is equals to 230 into 0.512 into cos phi, 0.0056. Here the value is 0.66 watts. Here the power factor is very less. That's why we are getting the power value is also less. Even though we are having 230 volts, the power which we are getting is 0.66 watts because of high impedance as well as low power factor. And we'll go with one more problem. When a coil of zero point 0.6 power factor, when a coil of zero point 0.6 power factor is in series with 100 microfarad capacitor. When a coil of 0.6 power factor is in series with 100 microfarad capacitor, when connected to a 50 Hz supply, the potential difference across the coil is equals to the potential difference across the capacitor. The potential difference across the coil is equals to the potential difference across the capacitor. Find the resistance and inductance of the coil. So the given data, let us write first. Cos phi power factor is given as, power factor of coil is given as 0.6, capacitance is given as 100 microfarad, and frequency is given as 50 Hz. Voltage across the coil is equals to voltage across the capacitance. And here the capacitance value is given. So first let us calculate the XC value. So that is equals to 1 by 2 pi Fc, which is equals to 1 by 2 pi into frequency is 50 and capacitance value is 100 microfarad, 100 into 10 to the power of minus 6, which is equals to 31.83 ohms. And voltage across the coil is equals to Vc, which is the condition given. I into Z coil is equals to I into Xc. From this we can write Z coil is equals to Xc, which is equals to 31.83 ohms. And we know that from the impedance triangle, from the impedance triangle, this is the Z, R, X. From the impedance triangle, Z is equals to, sorry, R by Z is equals to cos phi. R by Z, R by Z is equals to cos phi. When R by Z is equals to cos phi, we will get the resistance value R is equals to Z into cos phi. And here the Z value we got it as 31.83 because the condition is given Z coil is equals to XC. 31.83 into 0.6, that is equals to 19.09 ohms. After getting the resistance from the impedance formula, impedance Z is equals to square root of R square plus XL square. By using that formula, we are rewriting the formula as XL is equals to square root of Z square minus R square. Z square minus R square, where Z value is 31.83 square minus R square is 19.09 square, which is equals to 25.46. And here we got the reactance of the inductor, where we need to calculate, the inductance value. So here inductance value is equals to XL is equals to 2 pi FL. From this L is equals to 1 by 2 pi F into XL. This is not L, this is XL. So if we substitute the XL and frequency value here, 1 by 2 pi into frequency 50 and XL value is 25.46. That is equals to 0.081 Henries. This is the way we have to calculate the resistance and inductance of any given circuit. And next we'll go with one more problem, that is a resistance an inductance of 0.01 Henry and a capacitance are connected in series, when an alternating voltage V is equals to 400 sine 3000 t minus 20 degrees is applied to a series combination, which is RLC elements are connected in series, where the voltage applied is 400 3000 t minus 20 degrees is applied to the series combination. The current flowing through is 10 root 2 into sine 3000 t minus 65 degrees. Minus 65 degrees. Find the values of R and C. So here, for calculating the values of R and C, first let us take the phase angle difference, where phase angle difference phi is equals to 65 minus 20, which is equals to 45 degrees, and we are getting this as lagging condition. And now XL is equals to omega L, that is equals to, here the omega value is given as 3000. Here the omega value is given as 3000 into L, that is 0.01, that is equals to 30 ohms. And here tan phi is equals to tan 45, which is equals to 1. Where tan phi is equals to 1, that is, what is the tan phi value? XL minus XC by R, that is equals to 1. From this we can write it as R is equals to XL minus XC. R is equals to XL minus XC. So from this, Z is equals to Vm by Im. Here the Vm value is 400 divided by Im value is 10 root 2. These values are given in the voltage equation and in the current equation. So if we substitute these values, we are going to get 28.3 ohms. And if we get the Z, what is Z? Z is equals to square root of R square plus XL minus XC whole square, which we can write it as, from the above equation, R is equals to XL minus XC. In place of XL minus XC, we are writing the R. So R is equals to, that is, we are going to get root 2 times R is equals to 28.3, where R is equals to 20 ohms figure. And XL minus XC is equals to 20 ohms, where XC is equals to 30 minus 20, that is equals to 10 ohms, where C is equals to 1 by omega XC, that is equals to 1 by 3000 into 10, that is 33.3 microfarads. These are the different ways to calculate the resistance and inductance or capacitance values when some other data is given. Based on the requirement, we can calculate from the basic formulas. And here, this is another example which is used to calculate the supply voltage. Here the supply voltage is not given, the other parameters are given. Based on that, we have to calculate the supply voltage. So in series RLC circuit, which is connected across a 50 Hz supply, and the resistance of 100 ohms, inductance of 159.16 millihenry, and capacitance 63.7 microfarad. If the voltage across the capacitor is 150 at an angle minus 90 degrees volts, find the supply voltage. So here, first, based on the given data, let us calculate the current. After getting the current, we can calculate the supply voltage by calculating voltage across the resistance and voltage across the inductance. Here XL is equals to 2 pi FL, Here 2 pi into frequency 50 and inductance value is 159.16 into 10 to the power of minus 3, which is equals to 50 ohms. And XC is equals to 1 by 2 pi FC, that is equals to 1 by 2 pi into 50 into capacitance value is given as 63.7 into 10 to the power of minus 6. And here XC value also we got it as 50. So here VC is equals to I into minus JXC, that is equals to 150 at an angle minus 90, that is equal, that we can write it as minus J 150. And from this I is equals to minus J 150 by minus J XC. So J will get cancelled, 150 by 50, which is equals to 3 at an angle 0 degrees. This is the current which we are going to get. And now we are having XL, XC and resistance values. Let us calculate the impedance value. Impedance is equals to R plus J into XL minus XC, which is equals to 100 plus J into 50 minus 50, which is equals to 100 ohms, where V is equals to I into Z, that is 3 into 100, 300 ohms. This is the way we can calculate the source voltage. Now let us go with the power. In an AC circuit, the various powers can be classified as real or active power, reactive power, apparent power. Here in AC circuits, we are going to get S is equals to P plus J. S is equals to P plus J, where S is nothing but voltage into current, where P is equals to VI cos phi plus J VI sin phi. So here this P is nothing but the active power, Q is nothing but the reactive power, and S is nothing but the apparent power. So this is the way we are going to have the powers, that is active power, that is VI cos phi, and the reactive power will be VI sin phi, that is 90 degrees displacement to the active power. And here we can define the active power as the power due to the active component of current is called the active power or real power. It is denoted by P. That is, active component is nothing but real power, which where we are going to get is across the resistance. P is equals to VI cos phi, that is equals to I square R. The unit for real power is in watts. Now, the power due to reactive component of current is called as reactive power. It is denoted with Q, where Q is equals to VI sin phi, which is equals to I square into XL. Here, this value is because of the reactive component of current. So, the reactive power does not do any useful work. It is the circulating power in the L and C components. The unit for reactive power is volt ampere reactive. The unit for reactive power is volt ampere reactive. And the apparent power is the total power in the circuit. It is denoted by S, where S is equals to V into I, that is equals to I square Z. S is equals to square root of P square plus Q square. And this is corresponding to the AC circuits. In this session, we have discussed the RC series circuit and RLC series circuits along with some problems, and also the different components of power. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.